Hello, I'm so glad you could join us to wrap up our information on sine and cosine graphs, because today we need to talk about translations of the sine and cosine graphs. We already talked about in the previous podcast how to graph y equals sine x, how to graph y equals cosine x, and then we also looked at some basic things with vertical stretching and shrinking and horizontal stretching and shrinking. But we've not talked about translations yet, which is the movement left, right, up, down of a graph. So we're going to do that for sine and cosine today. I'll start my discussion with sine, and then cosine follows basically the same procedures. So I'll still talk a little bit about cosine too, but I'll start the discussion with sine. But just keep in mind that whatever I do with sine, cosine, the same kinds of things apply. Remember, they're sinusoidal. You take a sine graph and shift it, then you've got the cosine graphs. So they have the same kind of patterns and so forth. All right, let's say you have a sine function that fits this pattern. Okay, we already learned about a being the absolute value of the a there being the amplitude. Because basically, if you multiply the function by some number out front here, that number is going to have the effect of vertically stretching or shrinking the graph. And so, in this case, whatever number you're multiplying by, its absolute value is going to give you the amplitude. In other words, the distance of the maximum or minimum points from a horizontal line that cuts the graph in half. If you're vertically stretching by a factor of 3, your amplitude is going to be 3, because the distance between that horizontal line and the maximum will be 3 units. The distance between horizontal line and the minimum will be 3 units. But then we also had talked about period being 2 pi over this b, but that was back before we had a minus c in here. But remember, when we talked about period, we were talking about how when you're doing the sine or cosine, you're doing the sine or cosine of angle values from 0 to 2 pi. And you can do more. You can do bigger than 2 pi, less than 0. You can do negatives. But then you're going to have this repetitive cyclic quality of getting the same results. So for this discussion, we just need to think about 0 to 2 pi. But now instead of just having a b, the sine of bx minus c is going to fall within that interval, or some multiples of those numbers. And those multiples would end up coming back and giving the same answers anyway. So let's just go from 0 to 2 pi. An interesting thing happens when you solve for x here. So you add c across the board. And then you divide by b across the board. And you get this interesting result here. These values are going to tell you something about what's happening with the shifts and so forth of the graph. You still have the 2 pi over b for the period. That's going to tell you basically how wide the graph is before it starts to repeat. But then you've added in this c over b. And that c over b is a horizontal shift, where before you had 0 here on the left, now you have c over b. So the graph shifts horizontally from x equals 0 to x equals c over b. If c over b is positive, you have a shift to the right. If c over b is negative, you have a shift to the left. Or you can think about it too, like if you took y equals a sine bx minus c, and inside the parentheses here factored out b, factor out b, x minus c over b right here. It's just like an algebra class. If you add or subtract a number directly from the x in the equation, that's giving you a horizontal shift result. So here, if you're taking, the format is bx minus c. So here x minus c over b. So if you take c and b, and if it's written in the minus format, then take whatever c is and whatever b is without that minus. If that is positive, you're going to have a shift to the right. Because then you're going to have, your x values are going to have to be bigger in order to get your y values to come out the same. If c over b is negative, in other words, if you end up with like x minus a negative c over b, or in other words, x plus c over b, then it's going to shift to the left, because then you need x's here to be negative to compensate for adding that c over b. So you're going to shift over to the left in the negative direction. And you guys did that in algebra class with parabolas and circles and so forth, but that applies here too with sines. So you have a shift left or right. So this nice horizontal shift. So let's go ahead and take an example with some real numbers in it, and let's look at it. All right, let's say we want to graph a period, one period of y equals 3 sine of 2x minus pi over 3. And let's say they tell us to do this over the interval from pi over 6 to 7 pi over 6. Okay. If you want to help you see about the shifting, you could factor out the 2. This one's going to have an amplitude of 3, so we're going to have a vertical stretch by a factor of 3, because a, absolute value of 3, there's 3. That's the a. The period is still 2 pi over b, so 2 pi over 2, which is going to give us pi. And then in this case, the phase shift is going to be the it's going to be the c over b. So the pi over 3 over 2, which gives you pi over 6. And that's exactly what you see right here when you factor out the 2. Pi over 6 is being subtracted from x. X minus pi over 6 tells us there's going to be a phase shift to the right, pi over 6. And with sinusoidal graphs, when we talk about shifting left or right, we talk about, it's called the phase shift. I started just using that phrase, but that's what they call it here with sines and cosines. Okay, so with that data in mind, they said start with pi over 6 in the interval there. Well, pi over 6 minus pi over 6 is 0. You get 2 times 0, 0. Sine of 0, 0, 3 times 0, 0. So that starting point at the 0 was when x is pi over 6. Positive pi over 6, so it's a shift to the right, pi over 6. Then we're going to go all the way to 7 pi over 6 to do this. It's going to be our last point in the interval. 7 pi over 6. If you do that here, 7 pi over 6 minus pi over 6, you get 6 pi over 6, or pi. 2 pi, 2 times that's pi, 2 pi, and then the sine of 2 pi is 0 again. So it's like we're starting over. But then let's get some point, let's get a point halfway in between. That'll give us another x-intercept. So some key points here. If we take pi over 6 plus 7 pi over 6, we get 8 pi over 6 or 4 pi over 3. Divide by 2, we get 4 pi over 6 or 2 pi over 3. So that's going to be our middle value, and in the middle it's hitting 0 again. Halfway between pi over 6 and 2 pi over 3, you got 5 pi over 12. Just add these two together and divide by 2, and that'll give you a midpoint. If we put 5 pi over 12 in there, 5 pi over 12 minus 2 pi over 12 is 3 pi over 12, or pi over 4. times 2 is pi over 2. The sine of pi over 2 is 1. 1 times 3 is 3. And if we go halfway between 2 pi over 3 and 7 pi over 6, we got 11 pi over 12. 11 pi over 12 minus 2 pi over 12 will give you 9 pi over 12, or 3 pi over 4. Times 2 will give you 3 pi over 2. Sine of 3 pi over 2 is negative 1. Times 3 is negative 3. So we could have some key points. That's all we really need to sketch the graph, because this will give us a starting point and ending point, gives us our x-intercepts, a minimum and a maximum. That's all we really need. So let's go ahead and use those and go ahead and sketch this thing. Okay, so if the y's are 3, let's see here. 1, 2, I think I remember correctly, I can mark off 3 on this. If I do 1, 2, 3, 4, that's 2, and then 1, 2, 3, 4, there, that's 3. And then going down, 1, 2, 3, that's negative 1. Oops, sorry. I don't want the shape, I want to erase. Hold on, let's do this. I don't know, it erases the grid, but close enough. Okay. Negative 1, 1, 2, 3, negative 2, 1, 2, 3, and then negative 3 down here. Alright, and we need pi over 6. I accidentally marked that there. I didn't want to confuse. I keep hitting the tablet and it keeps doing that. Alright, we're marking off 5 of them. Let's see here. Pi over 6. 1, 2, 3, 4, 5. Yeah, it'll be fine. Okay. So if we put pi over 6 here, 5 pi over 12 here, 2 pi over 3 here, 11 pi over 12 here. You know what, I'm looking at this. That's not going to be spaced out properly. I have to be really careful. I want to space this out properly so I don't get a distorted view of what the graph's supposed to look like. So actually, what's going to happen, let me undo real quick here. Oh, that's going to take forever, isn't it? Yeah. Alright, let's do this. I'm just going to have to erase. That's right. I'm dealing with like pi over 12 of this. Let's see. If I have pi over 12, 2 pi over 12, this would be like 3 pi over 12, 4 pi over 12. Right here would be 5 pi over 12. This would be like 6 pi, 7 pi, 8 pi over 12, which is the same thing as 2 pi over 3. 9, 10, 11 pi over 12. 12, 13, 14 pi over 12, which is the same thing as 7 pi over 6. I gotta make sure to space this out because I don't want to distort the graph. Alright, that looks better. Okay, so pi over 6 we had 0. 5 pi over 12 we had 3. 2 pi over 3 we had 0. 11 pi over 12 we had negative 3. And 7 pi over 6 we had 0. Okay, let me just go ahead and connect with the smooth curve. If you want to do more points in between, you can. But these are enough to get a good sketch, so you can see basically what's going on with the graph. Good thing you can't see me while I'm drawing this because I have my tongue sticking out. Sometimes I stop and notice what I'm doing when I'm concentrating and sticking my tongue out, so you can't see that. Although I just told you, so anyways. So now you can laugh at me. Alright, there we go. And I remember this is cyclic. It means, it's going to repeat. So I didn't draw more than one period of it, but if you kept going, the periods would stay the same width, and then amplitude would stay the same, so forth. Looking closely at this, we have this horizontal axis right here. Distance from it to the maximum point is 3 units. Distance from it to the minimum point is 3 units. So that's that amplitude of 3. And normally the sine graph starts here, and then we're maxing out there. Trying to picture in my mind where everything would be. There. Let's see here. No, I'm losing track. I don't have it all marked out. All right, 2 pi over 12, 3 pi over 12, 4 pi, 2 pi over 12. This thing's weird. I gotta stop and think. I'm trying to think where pi over 2 and all that is. All right. Normally, let's see here. Oh, this one's really weird because 12 pi over 12 would be right here. This will be pi, so it's actually pretty stretched out. Okay. So pi would be there, and then pi over 2 would be 6 pi over 12. Oh, no wonder that's a 5, not a 3. No wonder I'm getting confused. 6 pi over 12, that would be right there. So on this particular grid, this is the beginnings of just y equals sine x. But what we have going on here is we have the vertical stretch by a factor of 3. So instead of maximum at 1, you have the maximum at 3. We have the period of this one being pi. So normally the period of your sine graph is 2 pi. Starts here, goes up at pi over 2, comes down, hits at pi, goes all the way down, minimize at 3 pi over 2, then goes back up and hits the axis again at 2 pi. Whereas the blue graph that we're graphing has a period of pi. So like if you go from the beginning point pi over 6 all the way through to the end point 7 pi over 6, the difference between those two is 6 pi over 6 or pi. So this has the effect of horizontally squishing it. Then you got the phase shift. Instead of starting at 0, we could start at pi over 6. Phase shift to the right, pi over 6. So that's some of the things that are happening to that particular graph. Okay, let's look at a cosine one so you can see, same kinds of process when you're trying to do the graphing. Black again. Okay, let's take y equals 3/2 cosine of 2x plus pi. And let's see about graphing that. The amplitude here is 3/2 or 1.5. So we're going to have that vertical stretch of 1.5. Then the period is going to be 2 pi divided by the b, which is 2 in this case, right here. So that ends up being pi. So we have a horizontal squish, because the period's only pi instead of 2 pi. It's not going to be stretched out 2 pi. And then the phase shift is c over b, which is going to be negative pi over 2. You might be wondering, well, where the heck did that negative come from? Well, remember the form is this: y equals a cosine of bx minus c. Just earlier we did sine, but we're just replacing it with cosine, and it's bx minus c. So if I want to rewrite this in the form, I have 3/2 cosine of 2x minus negative pi. so that I have that minus right there for the form. So then when I go to do the phase shift, that's c over b. C in this case is negative pi over b, which is 2. But you know, too, if you take it a little further, let's say you factor out that 2 in the parentheses there. Notice what you get. Factor out 2, you get x minus negative pi over 2. So negative pi over 2 is your horizontal shift. So you're going to be shifting to the left pi over 2 units. Because it's negative. Okay? Alright, so let's start with negative pi over 2 then. Since we're shifting to the left, instead of starting with 0, let's start with negative pi over 2 and figure out, let's see if we, and then if it's got a period of pi, take negative pi over 2 plus pi, you get positive pi over 2. So that'll give us some beginning and ending points for a period, graphing a period of this. Halfway between negative pi over 2 and pi over 2 is 0. Halfway between negative pi over 2 and 0 is negative pi over 4. Halfway between 0 and pi over 2 is pi over 4. Alright, so if we put negative pi over 2 in here, 2 times negative pi over 2 gives you negative pi, plus pi is 0, cosine of 0 is 1, times 3 halves gives you 3 halves. Then 2 times negative pi over 4 is going to give you negative pi over 2, plus pi is going to give you pi over 2. Cosine of pi over 2 is 0, times 3 halves is 0. 2 times 0 is 0, plus pi is pi. Yet cosine pi is going to be negative 1, times 3 halves is going to be negative 3 halves. Pi over 4 times 2 is pi over 2, plus pi is 3 pi over 2. Cosine of 3 pi over 2 is 0, times 3 halves is 0. And then pi over 2 times 2 is pi, plus pi is 2 pi. Cosine at 2 pi is 1, times 3 halves is 3 halves. So this will give us a good number of key points. Beginning, end, middle. It'll give us all the maxes and mins, and then between those, and we get the x-intercepts. Plot those graphs, see what it looks like. It's all good. Alright, so negative pi over 2. Let's see here. Let's do this. Let's make that negative pi over 2. Let's make that negative pi. So that means this will be negative pi over 4. This will be negative 3 pi over 4. Let's make that pi over 4. Let's make that pi over 2. Let's make that 3 pi over 4. And let's make that pi. And then marking off the y-axis, we got 1, 2. You can use whatever scale you want when you're marking off the axes. Just make sure you label everything so that people know what scale you're using and so forth. Alright, so negative pi over 2, we've got 3 halves, or 1 1/2, so that's going to put us right here. Negative pi over 4, we got 0. At 0, we got negative 1 1/2. Pi over 4, we got 0. And at pi over 2, we got 3 halves, or 1 1/2. With my scale, this is going to look kind of skinny, but you still get the idea about how to graph it. Okay, so there's the graph. The shift to the left, negative pi over 2. So normally the cosine graph would have started right here and then gone down. So negative pi over 2 shift to the left, and you see that point there. Then there's that vertical stretch of 3 halves, so instead of being at 1, you're at 1 1/2 right here. And then also normally, see, this would have gone this would have gone down, then come back up. So at 2 pi, this would have been back up to here. Pi, it would be down here. So normally it would have looked like this. So it would have been wider. But notice this is skinnier, but if you think about the fact that the period's only pi instead of 2 pi, it's going to have that horizontal squash. There you go. That's y equals 3/2 times cosine of 2x plus pi. Okay, so that's giving you horizontal or phase shift. Vertical shift, just like in algebra, how if you add or subtract something from the entire equation, you have a shift up or down. Well, that's the case here too, with sine or cosine. The d here, if you add or subtract something, in this case the d, the constant d causes vertical shifts. If d is positive, you're going to shift d units up. If d is negative, like if it's minus d, then you're going to shift absolute value of d units down. So the graph oscillates about y equals d. Instead of the x-axis. Which is y equals 0. So let's do an example. Let's say we're graphing y equals 2 times the cosine of x plus 1. The plus 1's there. There's no parentheses, so the plus 1 is separate from the cosine of x. We know the amplitude is 2. So we have a vertical stretch. The period is 2 pi over 1. There's a 1x here, 2 pi over 1 or 2 pi. Because it's just cosine x. So b is 1, c is 0. So the period's the usual typical 2 pi, and then the phase shift is 0 because there's no c there. But the plus 1 tells us that we have to shift up 1. So it's going to oscillate around y equals 1 when we graph it. Okay, so let's just do a quick little table here, and then we'll plot the dots and go from there. Let's go from 0 to 2 pi. Sorry, for some reason this thing's not responding correctly. There we go. 0 to 2 pi. Halfway between would be pi. Halfway between 0 and pi would be pi over 2. Halfway between pi and pi over 2 would be 3 pi over 2. Okay, 0. Cosine 0 is 1. 1 times 2 is 2. So you get the stretch of 2, but then you're adding another 1, so it shifts up to 3. Pi over 2. Cosine of pi over 2 is 0. Times 2 is 0. Plus 1 is 1. So instead of being at 0, we're shifted up 1. Pi, cosine pi, you're going to get negative 1 times 2 is negative 2. So that's the stretch, down 2. But then you're adding 1, shifting up, so you end up at negative 1 again. Cosine of 3 pi over 2 is 0, times 2 is 0, plus 1 is 1. And then 2 pi cosine 2 pi, you get 1, times 2 is 2, plus 1 is 3. Okay, so let's see about graphing that. Let's put pi over 2 right here. Let's put pi right here. Let's put 3 pi over 2 right here. Let's put 2 pi right here. Got 1, 2, 3. Negative 1, negative 2, negative 3. Switch over to blue. At 0, we got 3. At pi over 2, we got 1. At pi, we got negative 1. At 3 pi over 2, we got 1. And at 2 pi, we got 3. Again, this is just a sketch. It's close enough. Okay, and there's the graph. The graph oscillates about y equals 1, which is this horizontal line here. So where before these 2 points would have been x-intercepts, now they're all shifted up 1, so now the middle of the graph here cuts through y equals 1, because shifted up 1 unit. The original cosine graph would have been here, 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 and here. So you have, not only did it shift up 1, but then you also have that, or you can think about, okay, multiply by 2, this goes up to here, but then you have to shift up 1 still to go here. Multiply by 2, this stays put, but then shift up 1 to go here. Multiply by 2, you would get here, but then you have to shift up 1 and get back here. Multiply by 2, you get 0, but shift up 1. Multiply by 2, you get 2, and then you still have to shift up 1. And so you get that blue graph right there. And that's a little bit about the vertical shifts, up and down. Translations. Okay, so now you can handle graphs that do all kinds of things. You know, figure out what your amplitude is, figure out what your period is, figure out what your horizontal shift is, figure out what your vertical shift is. You can either start with the original graph and apply all those shifting rules, or you can do key points. You can figure out, well, with the phase shift, left or right, where would I start? And then with my period, where could I end one cycle? And then do a point in the middle, and then points in between those. So you end up doing like 5 key points and plot those and connect the dots. And that's another way to handle it. Okay, let me just conclude this with a real quick practical example of working with these lovely equations, these lovely functions. Let's say you have a situation where you've given Minneapolis's average temperatures. Apparently in Minneapolis in January it's about 13 degrees Fahrenheit. In April it's about 47 degrees Fahrenheit. In July it's around 73 degrees Fahrenheit, and in October it's 49 degrees Fahrenheit. For this Florida girl, that sounds cold. I can't imagine being 73 degrees in July, when usually we're like 103 degrees with humidity. But that's why I live here and not in Minneapolis, Minnesota. But anyways, okay. Let's take this and let's write a sine function of the form A times sine of bx minus c plus d. Or if you'd rather, you can say A times sine of b times x minus c over b plus d. You can do something like that. Okay, let's use these values to come up with a model here, a sine function. The reason I say sine function is because average temperatures are cyclic. If it's January, if it's an average of 13 degrees Fahrenheit in January this year, it's probably going to be close to that next year as well. So it's going to have this repetitive nature. So let's try to think about, well, if we can use sine, it's going to be cyclic. You're going to have your highs, you're going to have your lows. Summertime you go up high, wintertime you go down low, and then it comes back up. Summertime you go up high, wintertime you go back down low. And it just keeps doing that every year, year after year after year. So you might have year 1 to here, then you might have year 2 to there, and then you might have year 3 to there, and so on. So we're going to use sine. Probably the easiest thing to find first is the amplitude. Amplitude tells you the distance of your either your maximum point from this horizontal or your minimum point from that horizontal. So what we can do is take the maximum and minimum, see how far apart they are. In this case, the 73 degrees and the 13 degrees. See how far apart they are, and then divide by 2. Because you figure out how far apart they are, that's the distance between max and min. Then halfway between that is going to tell you your amplitude. So you got 60 degrees over 2, or 30 degrees. So A is going to be 2. Or 30, excuse me. So you got f of x equals 30 sine. Okay, so still have some more to fill out, but for now we got that. Okay, next, let's see here. Do we have a shift up or down? Is this centered around? This is not centered at y equals 0, because our temperatures are things like 13 and 73 and so forth. If we take the 13 and the 73 and find their average, that'll tell you what temperature's in the middle there, in between, right in the smack in between them. So you take 86 over 2, you get 43. This will help you to see about your vertical shift. So we're going to add a 43 on the end here for the vertical shift. I'm going to shift up 43. So the temperatures oscillate around 43 degrees, which if you think about it, your low is 13, your high is 73, and then in between April and October it's 47 and 49. That's not too far off from 43. So as you're moving up from the winter into the summer, halfway temperature is going to be around 43. As you're moving down from the summer into the winter, halfway temperature is going to be 43 as you're moving up and down. So it's going to oscillate around the 43 rather than 0. So you got plus 43 right there. Then for the period, this thing is cyclic for every 12 months. Every year has 12 months in it. So the period is actually 12. But then knowing that period is found by doing 2 pi over b, we can say, well, 2 pi over b has to equal 12. So b has to equal 2 pi over 12, or pi over 6. So we put pi over 6 right here. And then that finally leaves us with c over b. Trying to figure out what that's going to be. Let's see. Let's let January, coldest month, be x equals 1. Then when you come back to January, you know, right before that, yeah, x is 12. Hottest month is July. Let's let that be x equals 7. Halfway between is April. So halfway between there, x is 4. And then, like, if you went on to December, you'd have, for that, you'd have x is 12. And then October, it's halfway between and getting back to January here, x would be 13. October is halfway between July and January, which will give you x equals 10. So just thinking about like how this, where this would be situated on the graph. Like if January is 1, April would be 4, July would be 7. Let's sketch this real quickly here. Let's say we have, okay, 1, 2, 3, 4, 5, 6, 7. You get 1 here, 4 here, 7 here. January, it's a very low temp. April, you're here. July, you're up here. And then it starts to go back down again, like that, right? Okay. So we've already got our period. We know it's going to be we know it has to be 12. Let's see, 8, 9, 10, 11, 12, and 13 will take us back to January. Should be down here. Let's go ahead and do this some more. Like this. And we're doing a sine here. So we're looking at a phase shift. Like normally sine would start here. You go up, down, etc. But we have a phase shift. We could use this point as our starting point. So we basically have a phase shift of 4 to the right. So that means the c over b would be 4. That's our phase shift. So it's phase shift to the right. Okay, so you have that, and then you could rewrite that as 30. You can either leave like that, or you could rewrite it. You can distribute the pi over 6 and have pi over 6 minus 2 pi over 3 in there. Because phase shift of 4, that's the c over b, so that's right here. Minus 4. It's 4 to the right, so minus 4, because the form is minus. And there you go. There's your completed equation, your completed function to model what's happening in Minneapolis with their temperatures. Okay, so thank you for joining us, and I hope to see you again soon because we still have tangent and all the reciprocals to deal with.